Good afternoon, everyone. Welcome to IME 765. Today is April the 29th, and we're going to continue the regional Lasso regression today. And try to finish the Lasso, I think we can. First of all, let me stop the video here and share my screen as usual. Okay, so, put the annotate. No, where's my annotate panel here? I'm going to put my annotate panel here so that it's going to be more clear. Okay, so in the last lecture, we've mentioned Lasso regression. We've finished the ridge regression, the discussion of the ridge regression. Oh, by the way, in the very beginning of this class, everybody please make sure you download the newest version of lecture 11 from the Blackboard. I've updated lecture 11 a lot by adding the elastic net regularization to chapter 3, to section 3, and also added section 4, which is, in terms of Bayes view, Bayes estimation view, you're going to see actually ridge is the best. But that is a Bayes, just from different views to see the regressions and the shrinkage method. Okay, first of all, let's have a look at the Lasso regression. I know last time we've already mentioned it. Let's review it a little bit. So for the Lasso regression, it is the key is making this one to be one norm. You see it? This is one norm. Or you can see the corresponding Lagrange form. This is one norm. So that is the main difference between the Lasso and the ridge regression. One thing I want to mention here is that the same as ridge regression, here, my J starts from 1 rather than from 0, okay? And however, here, sorry, my fault. Here, you do have a beta 0, but here, in terms of your L1 regularization, it starts from 1. And also, also here, this is from 1, not from 0. So you need to be very careful that it's not just naturally, for example, I reformulate this problem to 11 to and 12 to 13 and 14, but we do need what? We do need a centering or shifting process. Okay, the shifting process is exactly the same as what we mentioned in sections 1.2, that we're gonna center y by yi equal to yi minus 1 bar, y bar, and also center each xij by xij minus xj bar. Well, where xj bar is the average of the jth column, okay? And by doing this, excuse me, by doing this, we can actually have a compact matrix form of the Lasso regression here, or the equivalent Lagrangian form here, okay? But just to let you know, here we do need what? We do need a shifting process rather than just naturally make it to be this way. This is the first thing. The second thing is that, well, I try to find the solution to Lasso, of course. So the very first thing I want to do is to have the normal equation. Remember what we did in in ridge regression? Here we go. We use this normal equation, right? And where is it from? It is actually from here. From this one, I differentiate it, and I do have this 8-2. I differentiate this one, and then I get my 8-2. 8a, sorry, and then from my 8a, of course, I get the solution of my ridge regression. But in your Lasso regression here, you do not have it. Why? Because of this. I remember I asked you last time, because beta norm 1 is not differentiable. Why? Because at 0, the point, the beta 1 norm, it looks like this way. Okay. So very clear at this point, it is not differentiable. Why not differentiable? Because according to the definition of derivative, you should what? You should have what? You should have your left derivative equal to your right. No, I should say the left limit equals to your right limit equals to derivative. But clearly, for this one, the left limit is -1, the right limit is +1. So you do not have a derivative. So that's a problem. So that you cannot just simply use a normal equation as what we did in the Lasso regression. And later you're gonna see this is actually the key, the most important part, the critical part of Lasso regression. Because of this, because it is not differentiable, so we will have the variable selection. And if it does have it, then you do not have variable selection. It's going to be a problem. Okay, let's see how to handle it. We will actually use the subgradient optimality condition to handle it. Let me ask you this. How many of you have not heard what's called subgradient here? The concept of subgradient have not learned. Oh, I just realized all of them turned off your video. Hey, let me see you guys, so that I know that you guys are really, listening to the class, rather than having a look at something else like Facebook. How many of you have not heard of subgradient?
I have not heard.
You've not heard? Arab also?
Yep.
How about Abdullah?
Hello.
Hello, Abdullah, are you there?
Yeah, I'm here. My video is not working. I don't know what happened.
You better update the installation. Probably it's by the installation problem. Anyway, okay. So by the way, Abdullah, have you heard of it? The subgradient?
Yeah, I heard that, but
Okay.
it's like solving convex problem, minimization problem, but I don't know the details that much.
Okay. First of all, what are the so you must have known it because your researcher have used it, especially in Exton's paper. He did use it, which is a super important conclusion. Could you please answer me a question? That is, why did people invent subgradient? What's the point?
What's the point?
Yes. Because
okay, so,
if we want to invent something, it must have some points, right? In some part, we can use it to solve some problem. Otherwise, why should we invent a new problem, right? So what is the point for subgradient?
So it's
subgradient gives always the underestimator of a function. So
of a convex function. Be careful, convex
function.
Yes.
So even if function is not convex, but we are interested to get a underestimator, like linearization, linear function, linear approximation of that function, then subgradient is helpful.
Very good. Yes. Actually, basically, that is the point. Because in some cases, your subgradient, first of all, theoretically, according to the definition here, from what I wrote here, you can see I didn't really say it is a convex function. So why just now I mentioned a convex function? The reason is because mostly if we apply the idea of subgradient, we're gonna make it to be the convex function. Otherwise, it's gonna be very weird. So first of all, let's have a look what is subgradient. For a given function f, which is not necessarily convex or differentiable, a direction S is called subgradient of f at x, denoted as, this is the partial, I mean the subgraph, means the subgradient of function f at x if and only if for any y in the domain ff, I have fy minus fx is greater than or equal to y minus x. Let's see what that means. Let me randomly draw something. Again, please excuse me if it's really too ugly. Let me draw anyway, it's really too ugly. What I want to do is something like this. I want to draw a line here. No, and then draw a curve here. It is a curve, okay? Suppose it's smooth. I know it's really ugly, but let's pretend it's smooth. Okay. And here's a point. So what I want to show you is this is a line and this is a convex curve. Okay. So for example, clearly at this point it's not differentiable, right? And then subgradient tells me that any S satisfy this one as a subgradient. So let's first have a look at the subgradient. Let me randomly draw a point. Let's see what is the subgradient. Let's use, for example, a purple one. Okay. Okay. What is the subgradient of this one? Oops. What is subgradient? Oh my goodness, please. What is the subgradient of this point? This is a point, not a circle, not a disk. Just I made it too large. Excuse me about my drawing capacity. So what is the subgradient of this one? So this tells you that any s direction. Let me use an arrow here. Any s direction that for any y, suppose y is from here to infinitively large. Okay, y is from here to infinitively large. We do not consider the left side. Okay, for any y, that fy minus fx is greater than or equals to this direction times y minus x. So for example, can I use this direction? You cannot. Can you give me an example? For example, if your y is here, then you're wrong. You're gonna make it less than y. See it? You need to have fy minus fx as greater than or equal to this s. S again is a direction, or you can consider it as tangent, whatever you want. A direction of y minus x. See it? And actually, in this point, your gradient gonna be in this direction. Subgradient is gonna be in this direction. In other words, the subgradient equals to the gradient. And we do have a general conclusion, which is actually very easy to prove, that if a function at one point is differentiable, then the subgradient must equal to the gradient. In other words, you have only one subgradient if it's differentiable. Question? Said, do you have a question? No? Okay. Let me mute you guys in case you guys are breathing or something. If you want to talk, please directly unmute yourself. Okay. Then the question is, what if something is in this direction? It's at this point. Let me make this point to be red point to make it more clear and make it bigger. Okay. No. I'm talking about a circle. Give me a circle here. Bigger. Okay. This is again a point. The point connects the line and the curve. Okay. So let's have a look at it. First of all, I can choose this direction, which is parallel to this line. Okay, parallel to this line. Why? Because very clear. For example, any y here. First of all, if any y here, it's going to be equal, right? Because this is a line. So of course, I have this conclusion. Okay, now let's consider if I have a y here. My x is here. This is my x. Okay, let me directly write it. This is my x. Okay, suppose I have a y here. Then isn't it the same? Then isn't it this is a subgraph? Why? Because think about this. This s tangent times y minus x gonna be in this length, this height, right? This is of course less than or equal to this height. See it? So that yes, this s1 is a subgradient. Okay, now have a look at this. How about this s2? Is it a subgradient? Is S2 a subgradient? Why not, Mahbuba? Give me a counter example. Mahbuba, I saw you nodded your head. So give me a counter example why it's not.
Okay, so the purple arrow, the origin of purple arrow, if we consider the origin of purple arrow as y, then
very good. Yes, then it's going to be the opposite case. Yes, because why? Be careful. Here it's going to be negative. Okay, the negative one is going to be what? It's going to be smaller. See it? If this is the y, this is the x. Y minus x is this direction, and times this one, I'm going to have this direction. See it? But what is fy times? So what I'm talking about is this. Y minus x is going to be this, and fy minus fx is going to be this. And this is bigger than this part, then something's wrong, So that's the reason why we cannot use this as the subgradient, so that S2 is not a subgradient. Then let me ask you, how about here? How about this direction? This direction is a tangent direction. Here, 3. This is a tangent direction. How about this tangent direction? Is it a subgradient? And actually, yes, this is still a subgradient. Why? Think about this. If y is here, very clear. Suppose I have a y here. So very clear. Oops, Oh, good, good. Very clear. This part is bigger than that part, right? So what if my y is here, for example? If your y is here towards this direction, you're gonna have this part. And if you really have a look at this part here, it's gonna be here. So you see, this one is still less than or equal to this one. It's negative, okay? And hence, yes, this is the direction. And actually, you can find, what you can find is any area in this part as a subgradient. Okay, so in this case, subgradient is not unique. Get a point? And let me ask you another example. How about this case? Let me draw lines. Say, what is that? A very big car, anyway. Suppose my function is like this way. How about a subgradient at, for example, this point? It's actually using the same idea. It's actually gonna be here. Let me use the red color. Be the region. Again, this is parallel to this line, okay, and this. So actually, you can see that any line in this area as a subgraph. So sorry, as a subgradient. Any direction in this area as a subgradient. Exactly the same. You just need to use this idea. So now, yes.
Not any line, but line have to pass
direction.
Ball.
What I mean is any direction in this area. Okay. Yeah, thank you. This is a good point. Not any line. It's not strict. I should say any direction. You are correct. Get the point? By direction, what I mean is, for example, suppose your original point is here. Suppose this is your original. Okay. By direction, what I mean is this. Let's suppose this one is parallel to this one, and suppose this one is parallel to this one. What I mean is this one, okay? The direction. It's not really a line. And usually what we do is that we can normalize it, make it to be a normal unit. And the direction is still the direction, you know what I mean? Let's say S11, S12, S13 until S1P, they're still the same. The ratio, I mean, still the same, but the summation of them, or let's say the norm of S, gonna be 1. So this is usually how people do about this. Any questions about the subgradient, the definition of subgradient? No? Okay. Now let's go back to the problem, to the question that we just discussed. So what is the point for subgradient? If we cannot use it to solve some problems, why should we have it, right? Okay, of course. Okay, let's have a look at this problem. So as we just mentioned, the subgradient is going to be something in this area. So this is the subgradient. First of all, this problem is not differentiable, so that I cannot directly use the gradient, the gradient descent method, which is find the gradient and then along the gradient go a little small direction, and then keep doing until I cannot really get too much improvement. The improvement is less than or equal to a given threshold, and then I stop. Okay, so by the way, Arab, this method you should have already seen it. A lot of numerical methods, no matter Newton or quasi-Newton, all of them use this method, okay, which is the descent direction method. Remember, I included in 770, which is lecture, I cannot remember, lecture 10 maybe. No. Lecture 13, I think. Yes, lecture 13, because lecture 12, lecture 11 or lecture 12, I introduced the Goldman's cut, which is about SBP application. And right after it, I introduced the numerical, optimization methods. So all of them actually are kind of like the descent direction, or should I say gradient descent method. But here, this is subgradient descent. Why? Because at this point, I don't have the gradient at all at this point. So what I'm gonna do is that I'm gonna kind of like move towards something here. You know what I mean? So this guy is the thing, what I'm gonna do. Now, by the subgradient, what we will have is we will have the subgradient optimality test. Oh, by the way, here let me mention this one because this one is related with the one norm. Suppose I have fx equals to x absolute value. So your fx looks like this way. They don't look like 45 degrees, whatever. Let me Let me change it. Let me make it to be this way. Let me see. Change the color to be blue, and okay, 45 degrees. So this is f equals to x absolute value, right? So let me ask you two questions. First, what is the subgradient at this point? The subgradient at this point is still 1, okay? Why? Because it is differentiable. If it's differentiable, the subgradient equal to the gradient. Now let's have a look at this point. What is the subgradient of this point? The subgradient of this point is anything between -1 and +1. Got a point? Anything from here to here. This one, the direction is +1. This one, the direction is -1. So it is any direction from +1 to -1. Okay? So this is a subgradient, and later we're going to really use it. Okay, now we have the subgradient optimality condition, which is if x star, it is here. If x star is a global minimizer of f, then this if is if. Then I must have 0 as a subgradient of f at this point. What does it mean? So let's have a look. For example, suppose my graph is like this way. Let's say this is my f, for example, whatever. It's like this way. Okay, now clearly this is your minimum point, right? And claim at this minimum point, direction 0 must be a subgradient. How to prove it? Super simple. First of all, if x is a minimum, so of course, if your x is 0, so fy is greater than or equal to fx. See it? So this is the if condition. How about the necessary condition? The necessary condition that if this is the case, then 0 must be inside. Because if 0 is not inside, in other words, this one does not exist, then so that you will have this one is not greater than or equal to 0, so that it's not the global minimum. So this tells you that 0 must be if and only if a subgradient of f at x star. See it? And this is the subgradient optimality test. Okay. First of all, any questions here? No? Okay. By the way, after the class, you do need to have a look at this. And for Arab, if you have never seen subgradient, I would strongly recommend you to Google it. Subgradient has a lot of great stories. Here, the one I'm mentioning here is actually just the KKT optimality, or you can call it KKT stationarity. Remember, the KKT includes of 3 or 4 parts. Remember it, and mostly for KKT, of course, the most important is the stationarity. So this conclusion is actually something similar to the KKT optimality. Okay, now let's have a look at this. Now suppose beta Lasso hat is a solution to Lasso problem 14. Again, to make our life easier, we're talking about the Lagrangian form, okay? So by the subgradient optimality test, if this is the minimizer, first of all, this is clearly the unique the global minimizer, okay? Get the point? Very clear, because this is what? This is convex, okay? And actually, this is, let me see, this one? No, I cannot claim it as. This is convex. So that's very clear, this problem must be what? This problem must be the global mean. The local mean equals to the global mean, right? Okay. Now, let's have a look at this. 0 as a subgradient of this. Okay, now let's really differentiate. By differentiate, what I mean is sub-differentiate. Doesn't really mean differentiate. Okay. Have a look at the first part. What is this? At this part, anything is differentiable, right? Because it's a quadratic function. Okay, so from here, what do we have? We simply have -2 xt times y minus x beta hat, right? Got a point here? Okay, now let's have a look at this, the second part. The second part is not differentiable. So what we're gonna write is to write it to be lambda s, where this s is a subgradient. Here we go, where it is here. S is a subgradient. So what does subgradient mean? One very important thing is this formula, okay? Subgradient of f1x plus f2x equals to subgradient of f1x plus f2x. So what we're gonna do is that the subgradient of this is, the first part is f1x, the second part is f2x. The subgradient of these two equals to the subgradient of this part plus the subgradient of the second part. See it? Okay, now we can make it to be this part plus this part, and S is a subgradient of this. In detail, I can write S in this way. So if your beta j is greater than 0, then my fj is 1. Why? Because of this. And this is your point. This is your 0 point here. If your beta j, for example, here, then of course the subgradient equals to what? Equals to 1, right? So your S equal to 1. If your beta j is this part is less than 0, your subgradient equals to what? Equals to -1. The question is, what if my beta j equals to 0? As we just mentioned, if your beta j equals to 0, then any sj, any direction in -1 and the +1 is a subgradient. So that here S is going to be any number between -1 and the +1. And then later you're going to see this is the key why Lasso is so powerful. Without this one, Lasso is nothing. Okay, and on the other hand, if I know Sj, can I know the beta j? Of course. Suppose your Sj, let's say, is a number strictly between -1 and the +1. You get what? You know that your beta j must be 0. Otherwise, it's impossible. But if your Sj equal to 1, you're going to say that your beta j is greater than or equal to 0. You cannot claim it must be greater than 0. Why? Because if beta j equals to 0, your Sj could also be 1. And also, if your Sj is -1, then you can conclude that beta j is less than or equal to 0. Okay, so this is some analysis from the optimality condition here. And then later you get to this point. Okay, now let's substitute 17a to 16b. This 16b is actually the optimality, subgradient optimality condition here. And if I substitute this Sj is in 1 inside, first of all, you're going to see what? First of all, if your beta is not 0, so that your Sj equal to what? Equal to the sign of beta j, SIGN. This sign, okay? Not sine, cosine, that sign. It's the sine function, okay? And so that you have what? You must have, so this is, I write it as the element decomposition. So this xtj comma, let's make it bigger. This one is this. I don't know whether you can see it more clear. So this notation indicates the jth row of xt, okay, of xt. In other words, this is actually the jth column of x. So I use this notation. This is for Arab, I think it's very comfortable because this is nothing but a standard MATLAB the notation, okay. And then, so I have this. I substitute 17a to 16. Then I have, you know, -2 canceled. This becomes negative lambda s. Move this one to the right-hand side. So because my beta j is not equal to 0, so lambda times sj equals to what? Equal to lambda times sine of beta j hat. And then the left-hand side become what? Becomes the jth row of xt. And then I have this one, 18a. If my beta j is not equal to 0. But what if my beta j equals to 0? Okay, if your beta j equals to 0, as we just mentioned, your Sj is going to be between -1 and +1, right? Okay, so that you have this part equal to lambda times a number as between -1 and +1. And what we can do is add an absolute value, and this part must be less than or equal to lambda. See the point here? So actually, as long as I substitute a 17a to 16b, I get 18. Any questions here? This is very important. Because of this, later we have a lot of analysis about Lasso. Get a point here. By the way, Mahbooba and Abdullah, no, let me see. I don't know whether I asked Mahbooba to do it, but for Abdullah, I'm 100% sure I asked you to write the Lasso part. Did you include these parts from 16 to 18 in your report? I forgot at that time. Because if you did the Lasso very carefully.
You did not ask me.
I didn't. So Abdullah, I asked you, right?
Yeah, you asked me.
Did you finish all these parts? These are very, very critical, because why Lasso is so good? What is the point? Everything's from here, because it's not a differentiate. If it's differentiate, then no difference from the ridge actually. Just because it's not differentiate and it has so great properties, then later you're gonna see it does have the function of what? Of variable selection. Okay. So far, any questions? Regarding the math details, you need to have a look very careful, calculate it very carefully by your hand after the class. Again, I'm not gonna, show it step by step. I just give you the rough idea. Okay. The detailed derivative, derivation, you should do after the class, step by step by yourself, rather than just accept it. No, as I told you before, try to challenge it rather than try to accept it. Okay. Now we have this. Now let's have a look. Why Lasso has the function of variable selection and also shrinkage. Okay, let A be the support, or let's say be the active set. I know in the best subset selection, I use the set S, because S means subset selection. Similar, you can use S or A here. I use the A here as because most of textbooks, they use the A here to indicate it's the active set. For my personal notation, I want to call it support, so that I use S, whatever. And then let this A be the active set of Lasso regression. In other words, if J, the index J is in A, then beta J is not equal to 0. If J is not in A, then beta J is 0. Okay. So why I want to discuss these two cases, beta J equal to 0 or not equal to 0, because of this. Because of this. See here? From here and here. From 17 to 18, you can clearly see. I do need to discuss whether beta J is 0 or not, because the subgradient gives me the difference, the big difference. If beta J is not 0, then it's differentiable. If it's differentiable, you can play whatever you like. It's more like a ridge. But if beta J equal to 0, it's not differentiable. And hence, you're going to have 18b instead of 18a. See it? And that's the reason why here I do need to discuss what is its support, or what is its active set. Okay? Now let's have a look. If I have this A index set to be the active set of Lasso regression, what's going to happen? So first of all, let XA to be the columns of X. This alpha J is the J's column of X, in which the J is in A, is a support column. So that XJ means what? It's a subset of S, in which all columns are are in the active set. Okay. Then very clearly for this XA and the corresponding beta A, I have what? I must have the normal equations, right? Because this tells you that everything here is differentiable. Your beta is not 0, so of course it's differentiable. So simpler, I just do the normal equations, something like this. And by the way, here I still need to be careful because what? Because here I apply the 16b and also the 17a. So I just plug in everything in this way here. Now I have this, but I didn't just write it, as that form. Again, make sure you use the newest version, okay? Because in the previous version, I actually made a mistake here. I wrote it just randomly, and I carefully checked it. I realized mathematically it is something wrong. Make sure you're using the newest lecture notes. You can download it from the Blackboard. Okay. Now here you cannot simply write it as MP. MP is a latex. Latex. MP means this. It's a latex command. Negative minus plus. Previously, I remember I write it to be negative minus plus lambda SA, which is not correct. Why? Because the minus plus, the meaning here is that in each element in terms of S. S1, SA1, SA2, SA3. Each of them can be minus plus, rather than the whole to be minus plus. You know what I mean? For example, SA1 can be minus, SA2 can be plus, SA3 can be minus. So I cannot, previously I just wrote S minus plus before my lambda. It's not correct. Okay, now here, from here, I can of course calculate my beta A. Beta A is this. Okay, again, I assume this inverse exists, of course. And the beta A bar is the complement of A, is 0. This is by my definition. If beta J is not in A, then it is 0. Okay, now, of course, we're going to focus on 20A. Let's see what 20A is going to give us. So the thing here is that I have beta A equal to this part, and actually you can see, guys, what is this part? This is nothing but the what? Least square solution. See it? It is the least square solution. So actually, this tells you that for a support element or for an active element, this equals to the support the least square solution minus this part. See it? This part times, of course, the XAT XA inverse. And hence, we can see we have a shrinkage here. Get the point here? Then you may ask me 2 questions. First of all, okay, I can see the shrinkage, but where is the subset selection? Or let's say, where is the variable selection? Second, don't you feel something very weird here? Do you have any questions regarding 20A, the formulation itself? See this. Here is beta A, beta hat A equals to something. And in your right-hand side, you have sine beta hat A. See it? That's why I wrote here, attentive readers may say that, hey, here's something wrong. How can you make itself with itself? The left-hand side and the right-hand side, both of them includes the beta A. See it? And it seems that we have a logic issue here. And the truth is that, no, we do not have logic issue. The truth is that, think about this. This means what? This means, first of all, this is not an explicit solution. And unfortunately for Lasso, we do not have such a closed form explicit formulation. And that's also the reason why in the name here, I call it, I cited, see it? The so-called solution to Lasso, because it's not an accurate or a closed form Lasso solution, which is this 20A. But 20A does give us a lot of information of Lasso. What are these information? It is given by this, lambda times sine of beta A. Here's the point. So why there's no logical issue here? So you can consider it in this way. First of all, here we go. Here's the part that I fixed, the problem here. First of all, I can always write a beta A to be this way. And this part, I know this notation is kind of wrong. I created it by myself. Probably you've never seen it in any other books. As long as you understand the meaning, it doesn't matter what does it look like. So this part means this is a 1 vector, but each element could be -1 or +1. Okay, it doesn't mean that all of them should be positive or -1. Okay, it means it's a free. You know what I mean? So totally, I have 2 to the power of p possibilities because each one has 2 choices, +1 or -1, right? Okay. So first of all, very clear, this beta A is in this form. This is for sure, right? Because it depends on your beta J, beta AJ, whatever beta AJ looks like, then I have this. By the way, what does sine beta A mean? Sine beta A simply means this, okay? Anyway, no. Let me use a word. I really cannot tolerate this. It's too difficult to write. Really, really difficult to write. Let me open a Word document. So here, so here, sine beta A this is a vector, okay? This means this means this. begin B matrix, and here are 3 rows. This means this sine of beta A, let's say, let me write it in this way, beta A1, and the sine P. Okay, it means this, it's a vector, so that you can clearly see each element is gonna be either +1 or -1. See it? It's very clear. So that here I must have this. I must have beta A equal to this part by 21. The question is how to determine for each one whether it's +1 or -1. And guys, after this class, right after it, please think about this problem very carefully. You need to spend at least hours to think about this. This is really, really the very, very beautiful point. From here, you can see the wisdom of human beings, not only one person. This looks like it has a logic problem, but this is super beautiful. Think about this. Suppose I have a beta AJ, and suppose I have this part. Suppose I let everything, for example, everything to be, let's say, positive, let's say. And then I have, let's say I have a positive lambda here, and this part plus positive lambda, it is still positive. Then you have what? Then for sure you get the for sure you get this sine beta A J to be +1. If add this part it's negative, then for sure you get it equal to -1. But what if it is between them? Then you may have a problem. You know what I mean? Because if it is between them, which one should I choose? In other words, here I'm asking the question is how to set up the positive or -1 here, which means the sine of beta A itself. You know what I mean? I need to determine this part and to determine itself. But this part itself is determined by itself. You know what I mean? That's why I said here, give me 5 seconds. That's why what I said, this might cause a logical problem. Yes, Said.
Why in 21, the second part of beta hat A, it's plus lambda.
Because I write it to be negative plus rather than I write it to be minus plus rather than plus minus. You know what I mean? So when your sine beta A chooses 1, then it's going to be minus. When your sine beta A chooses -1, then it's going to be plus. It's MP, not a PM. You know what I mean? Minus plus. I'm talking about this part. It's minus plus. See it? Here I write it to be plus to make it easier. Otherwise, I'm gonna have a negative plus minus. I feel it's more confusing. So I change it to be plus minus plus. That's the reason.
Okay.
Yep. Yeah. And you need to think about this. This is very, very important and a very, very beautiful idea. So here I directly introduce you the conclusion. Okay, think, really, really please think and challenge it after the class. By this way, you can really learn rather than just accept it. Okay, so excuse me. So the basic thing here is I just need to determine the sign, negative or positive. And the point is that we can theoretically try all possible combinations. How many combinations do we have? We have 2 to the power of p. And it doesn't matter how large p is, as long as p is finite. 2 to the power of p is finite, isn't it? I'm talking about theoretically, right? It's finite. So theoretically, I can try all of these possibilities and then figure out the settings of the sign. Am I correct? You know what I mean? So what I mean is that, okay, so let's consider a J. Suppose beta AJ, you think it's a positive, suppose, okay? Then you just plug in this positive and substitute inside to see whether it's really correct. If it's correct, then it's fixed. If it's not correct, then you change the other option. And be careful that it's correlated with other selections. So theoretically, how many possibilities do I have to try? I have to try 2 to the power of p, 2 to the power of p possibilities. But it doesn't matter. Here, my point is just exist. I don't care how exactly I choose it. Actually, when people do it, people use the LARS, the least angle regression to choose it, which is actually a forward stepwise method. But here, I just let you know that I can do it theoretically. Okay. Then the question is, well, assume that you can set up this sine beta hat A. The question is the setting unique? Because if it's not unique, then I'm going to have a chaos, right? And fortunately, yes, it's unique. In the paper here, it's already showed that as long as your A, XA has a full column, then the Lasso solution is unique. In other words, you must have exactly one setting for this, or for this, for the sine of beta A. Actually, you can use a very simple way to understand this. Why? In terms of optimization, forget about statistics. As again, machine learning equals to OR plus statistics. Just think about the optimization part. Question, is this problem unique? It is unique, see it? And I'm done. Get a point? That tells you that as long as your X is a full rank, it is unique. The setting here is unique. In other words, you will have exactly one solution for the setting up of the sine beta A. Okay, and why we have the what variable selection here? For the shrinkage, you've already seen. This is the shrinkage part. Why we have the subset selection? Why we have the variable selection here? Algebraically, here we go. Because you need to choose the support vector, the active set vector. And for things not in active set, you're gonna have this, in which you need to choose the sine of beta. This actually, when we are really doing it, we can do it polynomially. Nobody's gonna really stupidly, do this. Nobody's gonna do it. The stepwise method can really solve it. The least regression, least angle regression can solve it. Okay, but you do need to choose the A. You know what I mean? And for this part, actually remember the forward stepwise selection, which is used to estimate the subset selection. Remember it? You're gonna do what? Using a greedy method, choose the column that's gonna what? That's gonna maximally reduce the RSS in the columns remaining, in the remaining columns. Remember it? So in this case, I'm gonna choose that column. The same here, the least angle. Okay. If you're interested, please read this part, because if I add it, I want to kind of like introduce very clear about it, but it's gonna take a lot of time. I don't have time to introduce this. It is in chapter 344. Or you can just read this part. By the way, this is highly recommended. Ryan Tipashirani, the son, not Robert Tipashirani, wrote a very, very beautiful, let's say, introduction part of the Lasso. Highly recommend you to read this. Okay, so that I've showed that this one is unique. And for the for the variable selection part, it is by choosing this subset, this active set A. And by the shrinkage, it's by this negative lambda times sine of beta A. Okay, and that's why Lasso has two functions, both variable selection and shrinkage, which is I wrote it in red here. Okay, and actually this part we can see, for example, where is it really this one from? From negative lambda sine beta A. These are from where? From 17 and 18. See it? It's from this S, and hence I do have a variable selection here. Get a point here? So you can read the point here. That's exactly what I just talked. Variable selection plus shrinkage. Okay, any questions here? Probably you have a lot of questions, but maybe you haven't read it carefully. Please do read it very carefully. Okay, after reading it, if you have any questions, please go to my office hours. Virtual office hours, not the real office hours, which is every Monday, Wednesday, right after the machine learning class. Okay, then you can ask me either by appointment or let's say office hours next week. You should have a lot of questions. Otherwise, something's wrong. Otherwise, probably you didn't read it carefully enough. Okay, then let's introduce again a special case, which is if X columns are orthonormal, the same as we did here. Where where's my ridge regression here? Okay, here, this part. If my X columns are orthonormal, we have seen that the ridge regression can be expressed in this way. Okay, now let's have a look what's going to happen for the Lasso regression. For Lasso regression, if X columns are orthonormal, then we actually can write a closed form. Why? Let's have a look at this. So first of all, continue this one, something similar here. I think here I borrowed from this part, 16b. So this is the same as 16b. I have this one, right? Okay. Now I discuss from here, and I get this. The beta Lasso equals to this. Why? Because X has orthonormal columns, so that I have xt equal to I. Okay. So for example, you have a look at this 18b here. What do you see? You have xty minus xt times x, which is I, so that you have I times beta equal to lambda s. See it? And hence your beta equals to what? Your beta equals to xty minus lambda s. Get a point here? So which is exactly here. Okay? Your beta Lasso equals to this. And have a look at this. What is this part? This part is actually your least square solution. Why? Because again, xtx as I. So you don't need the first part, xtx inverse. So your least square solution directly equals to xty, right? And the least square solution is a constant. So I write it as a constant. So it equals to the least square solution minus lambda s, where s is defined here. No, not here, above, here. Where s is defined here. F greater than 0, then 1. F beta is less than 0, then negative 1. F beta is 0, then any number in this interval. Okay. Now let's discuss the three cases, which is beta is greater than, less than, or equal to 0. Okay. If beta is greater than 0, what do I have? I have this one equal to this one minus lambda. It's greater than 0, so that I have OLSJ must be greater than lambda. For the second case, if my beta j is less than 0, so this is less than 0, so that I have what? I have this one is less than or equal to negative lambda. What if your Lasso j, beta j equal to 0? If it's equal to 0, so I have this. And if this case, as we just mentioned, we move this part there, because s is what? S is any number between -1 and the +1. A -1 and a +1, and the lambda is a positive number, okay? Lambda is positive. Here, we do not consider lambda as 0, which is a triple case, meaningless. We consider lambda as positive. So in this case, I will have OLSJ equal to lambda times Sj. In other words, I must have what? I must have the absolute value of my beta OLSJ is less than or equal to lambda. See it? Okay. Then I can conclude these 23 A, B, C, three cases in only one formula, which is really powerful in this way. See here? The left, this part is the sign of this OLS beta J. By the way, OLS beta J, this means the jth element of OLS beta, okay? Times, this means if it is greater than 0, then it's this number. If it's less than 0, then it's 0. Okay, as I defined here, see it? The operator, this plus equal to x, if x is greater than 0. And if it's less than 0, if x is less than or equal to 0, then it's equal to 0. And you can easily verify it, 23 A, B, C. No matter which case, this 24 is correct. And hence, this 24 is my explicit or my closed form solution of my Lasso estimation for this special case, okay? For this special case. By the way, strongly recommend you try to get this by yourself. And to let you know, when I wrote the lecture notes here, I directly saw this solution from ELS, Elements of Statistical Learning, but I really dislike it. So I try to write another form by myself, and then maybe you're gonna laugh. Maybe you're gonna laugh. Just this part cost me about 40 minutes to try to get it by myself, because I really don't. I try to say that this is not beautiful. I try to write a more beautiful form, and really ironically, finally when I finished it, and then I opened the book, and they're exactly the same. Well, I tried my best, and however, to be honest, I still feel maybe there exists a more beautiful solution there. Guys, try to challenge it again. Try to challenge it. I failed. I hope you guys can be successful about it. However, I'm kind of lazy as I already got it by myself. You know, how I got it exactly by these 3 steps. I mean, these steps are done by myself. That's how I got it. I just discussed 3 cases, and then I try to write one formula to make everything to be the same. One reason you have to write the sign here is because of this. You have an absolute value here. See it? So it's no choice. You have to write a sign here. Okay. And you may ask me, so why you write this part? This part because for this part, because your beta 0 could be 0. So that finally you're going to use this part to indicate this part. So again, you can see the problem is in the case for beta equals to 0. Again, it is what? Variable selection. See it? It is really variable selection. Any questions here about this specific case? This part it's tricky, but not difficult. To be honest, I believe all of you can do it. But the problem is you really, really need to do it. You know what I mean? Rather than just accept it. No, you need to do it by your hand, by your method. Okay, so after that, let's introduce a geometric interpretation of Lasso. This is more intuitive than the Lasso, the theoretical part here. Okay, first of all, this diamond part is what? Is the Lasso constraints here. And everybody, please pay attention here. This part is very, very important. And it's gonna really save your time if you can understand the geometric part very well. So this shaded area is the diamond, which is actually beta norm less than or equal to t. Very simple. Of course, here I have only 2 betas, beta 1, beta 2. So it becomes this. And as we just mentioned, as we mentioned in the previous class, suppose the beta OLS, the ordinary least square solution is here, and the contours are what? Are ellipse. For the reason, check here, check section 1.3, I think, geometric interpretation. See it? So this is again a conic expression. For the conic expression, this part, the quadratic part, is what? The determinant is greater than 0. Okay, and hence this must be what? This must be an ellipse. What if it equals to 0? It must be a power. Anyway, it must be in this way. Okay. What if it's less than 0? It must be in this way. Okay. Okay. I need to review a little bit about the English terms of these kind of math things. Anyway, so here because xtx, it is what? Positive definite. So the determinant must be 0 or greater than 0, and hence it must be, the contour must be ellipse. Okay, then the contour's ellipse. Have a look at this, guys. Here the center, I'm gonna gradually make my contours bigger, 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 until what? I'm gonna stop. Until the first point that I reach here. I cannot say here. I reach kind of like a tangent, or the first point that I contact with this shaded area, right? For example here, and hence I call this is a Lasso solution. This is correct, right? Any question here? Just exactly the same as the ridge regression here. See it? In the ridge regression, what did we do? Oops. In the ridge regression, what did we do? I also start from here and I gradually increase my contour bigger, bigger, because the contour increasing means my RSS is increasing. I want to get my minimum RSS, so I'm going to choose the first point that it touches the feasible region, and this is going to be the ridge solution. Similar here, the Lasso, I'm going to choose the first point that I'm going to touch this diamond, right? Okay, now guys, have a look. First of all, where is the shrinkage? The shrinkage part, because previously it's this large. Now it is this large, and hence it's a shrinkage. It's smaller, see it? And the most important, the more important is why it is variable selection. Because, have a look at here, what does this beta Lasso mean? This beta Lasso means beta 1 equal to 0. See it? In other words, yes, you did select the variable that you only choose beta 2. You dropped beta 1 already. See the point? That's why Lasso has both. That's why Lasso has both shrinkage, which is from here to here, it's smaller, and also variable solution, the variable selection that it drops this beta to 1. It only has beta 2 here. See it? This is extremely important. And if you draw the picture here, draw the plot the contour and also the feasible region here, this is so intuitive. See it? This explanation is very, very intuitive. And you may say, oh, it looks really simple. It's not simple. This idea cost people how many years? About 20, 30 years. And this is one of the greatest invention, the greatest creative work in 20th century in statistics, one of them. And it's a big, revolutionary, a milestone, really a milestone. And in this picture, it interprets just so simply. See it? Shrinkage plus variable selection. Clear? Any questions here? Make sure you understand it very clear. However, one thing I want to say that it's not always this point. You know what I mean? So for example, suppose your eclipse can be in this way, for example. Anyway, let me draw it by my hand. Again, please excuse me if it's so too ugly. It can be something like this way. For oh my goodness. Anyway, let me change the color. Let me, for example, it can be something like this way. In this case, then here's going to be your your Lasso regression. So in this case, although I have the shrinkage, I do not have subset. I do not have variable selection. See it? What I mean is that it could have variable selection. I didn't say that it will always have variable selection. Okay, be careful about the logic here. However, the good point is that here, because I have my beta is 2D. If my beta is p dimensions, so I have more and more and more what? This kind of points, the corners. When I have more and more and more corners, it's more and more possible that my Lasso solution is gonna, gonna be obtained at the corner. At the corner means what? Variable reduction. Okay, so this shows you the power, very actually intuitively shows you the power of Lasso regression, which is both variable selection and shrinkage. Okay, everything's here. And that's also the reason why we call it Lasso. Lasso means what? I don't remember. Lasso means, okay. There's the least absolute shrinkage and the selection operator. So this is the full name of Lasso. By the way, in terms of English, what is the Lasso? Do you know it? It's something like a collar, on, let's say, the neck of a horse. That is the Lasso. Something, to control the horse. But here, Lasso is the least absolute shrinkage and selection operator. Okay, Lasso. Any questions here? No? Okay. The next thing, still in this section, I just skipped, and I want to mention here is how to solve Lasso. The first method is the statistical method, which is Lars. As I mentioned, I don't want to spend too much time here, which is nothing but a forward stepwise selection method. You can always select what? The one with the least angle. In other words, it's gonna be the smallest angle with your current residue, which is very similar to this idea, almost the same as this idea, which is here. Let me see. Remember here I said many people wrote in that way and they think they're the same. Actually, they're different. Remember here? This formulation that I got by myself here. Here, remember this part? This is lecture 10. I'm talking about lecture 10, okay? And then I wrote this part. Many people do it by this way, see it? And this is the basic idea of least angle, the least angle regression. Why? Because it is in this way. Suppose this is my current y minus yl. I have so many different options. Let me use a different color, sorry. The red color means the current residue, which is a y minus y hat l minus 1. And the other residue, my columns left are something like this. And which column I'm gonna choose? Wait. Suppose they are the same length. I need to make it Otherwise, something's wrong. You know, suppose they're the same length, okay? The same length. Which I'm gonna choose? I'm gonna choose this one. I'm gonna choose this one. Why I'm gonna choose this one? I'm gonna choose this. Oops. I'm gonna choose this. Let me make it bigger. Why I'm gonna choose this? Because this is the most parallel to this. In other words, if I choose this, I'm gonna make it, you know, the reduction the most. And in other words, this the most parallel means what? Most, this angle is the smallest. And hence, this is the least angle regression. See it? So the basic idea is right here. And let's see. For the details about the algebraic, you know, calculations, please refer to the book. You know, actually, as long as you get this point, you can just do it by yourself. You don't have to really read it. Try to invent it by yourself. Really easy. Okay. The second method is ADMM. For example, Mahbouba, can you use about 30 seconds to introduce what is ADMM? The alternative. What is ADMM? I cannot remember the full name. Alternating direction method of multipliers. Yes, Mahbouba.
So ADMM is a method that can use to solve optimization problems.
Of course.
So generally in optimization problems, we have one function. So if we have separable function in our objective function of an optimization problem, and if we want to solve those separable functions individually and combine the solution together, then ADMM counts. So it takes advantage of
yes. First of all, Mahbouba is correct. Sorry for interrupt you, because I don't have enough time. Let me finish it. What you said were correct. It's just kind of too long. So in conclusion, ADM has mainly two functions. The first function is that it has it has the decomposable x. Okay, why I care about decomposition here? Because have a look at the Lasso. Lasso looks like this way. See, the summation of so many yi, y2, y3, y4, and also here beta 1, beta 2, beta 3, beta 4 till beta p. I want to decompose it to be one. I mean, for each I want to solve it, or for each j, I want to solve it first. So this is decomposable, which is the first benefit or the first advantage of what? Of ADMM, where it is, in which the update of x is decomposable. The second thing, this is from the dual descent accent method, and the dual gradient accent method. And the second thing is the ALM, the augmented method, which has a weaker condition and a better convergence property. For the first part, it needs to be strong convex. And it has a serious problem that if the problem is not strictly convex, then you may not be able to do this. So ADMM actually combines these two parts. And it's very, very good for these kind of problems, which are convex, but not strictly convex, and which are decomposable, which means it's a summation of I from 1 to, for example, P or from to N, the summation of different parts. Okay. Regarding the details of ADMM, please refer to here 5. 5 is, I think I cited Boyd. Yes, Boyd, Stephen Boyd. This is a very, very good introductory or the fundamental, the basic level of understanding the ADMM. Later, if you have finished it, especially in summer, you should have a lot of time to read, to study. Please do it. If you have finished most part of it and you have more questions, please ask Mahbouba, let's say. Please ask Mahbouba. And he will give you more papers to read, especially X10's paper. Strongly recommend you. Really, really beautiful. And I personally like X10's paper more than this part. But this part is more complete, much more complete than X10's paper. Okay, so that here we introduce 2 more methods. The ADMM method is a pure OR method. There's no statistics part here, okay? It's a tool, very powerful and a relatively modern tool for solving this kind of convex, decomposable convex province. And the Lars here, the least angle regression, is actually a statistical method. Anyway, as long as you can solve Lasso, it doesn't matter. Again, machine learning is statistics plus operations research. Okay, so here's everything about the Lasso part. After it, let's have a very simple comparison between the Lasso and the ridge regression. First of all, let's have a look at the case again when X is also has orthonormal columns. From what we let me see. From what we have seen from let me see. What is this part? Okay, this part is the best subselection part. From what we have got in 24. So 24 here, this is the Lasso explicit or closed form solution for these X columns when X columns are orthonormal. And then after it, where is my ridge conclusion? My ridge conclusion is here. Where's the ridge conclusion? The ridge solution is here. Okay, this 9 is the ridge solution. And you can see what? You can see in the ridge solution, actually it does what? It does a shrinkage, just a shrinkage from the least square solution. See it? By a factor of 1 plus lambda, right? Okay, now have a look at Lasso. What does Lasso do? Lasso first has a shrinkage. The second thing, it has a what? It has a drop, a truncation. See it? By this plus. If the absolute value of this OLSJ of beta is less than lambda, I drop this part. If it's greater than, okay, so I don't drop this part. See it? In other words, I'm comparing this OLSJ with the lambda. See it? By the way, lambda is a user-defined parameter, okay? And we call it as a soft thresholding method, which is I compare this one with a parameter, user-defined parameter. I drop it here if and only if the absolute value of the jth element of your OLS solution is less than lambda. That's why I call it, it's a closed form, because everything is known. Lambda is known. OLS solution, of course, it's a constant. So it's a closed form. Now let's have a look. What does the best subset selection look like? Okay, first of all, we write in this way. Let me make it bigger to make it more clear. First of all, we write the best subset selection in this way, which is this times this, and wait. Oh, okay, so sorry, made a mistake. I should say this. If J is selected, if J is selected, then BSSJ, the beta SSJ, the beta BSSJ, which means the solution of the best subset selection, the jth element equals to the jth element of OLS, right? If it's selected, of course. Now, otherwise, if it is jth element is not selected, then it equals to 0. Then the thing is what? The thing is, let's calculate the RSS. Since RSS is in this way, to minimize the RSS in the subset selection here, what you're going to do? You're going to clearly choose what? Because you must choose at most k elements to be non-zero. All others must be 0, right? And so let me ask you, which k will you choose here? The biggest k. Right? Why? Because in this case, you're going to minus the most, reduce the most. You know what I mean? This is a constant, right? And this part means what? This part means minus the square of beta OLS1 plus square of beta OLS2 plus blah, 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 plus a square of beta OLSP, right? And among these P beta OLS elements, only k of them are non-linear, are non-zero. All others are 0. So let me ask you, which k would you choose to be non-zero? You're gonna, of course, choose k, which has the maximum absolute value of the beta. Get a point here? Suppose, let me give you an example. Suppose beta 1 equals to negative 0.9, beta 2 equals to 10, beta 3 equals to, let's say, 3. And I let you choose 1. to be non-zero. Both all others are 0. Which one will you choose? You're going to choose beta 2 equals to 10, right? Because in this case, I'm going to minus 10 squared. Otherwise, because I can only let one beta to be non-zero, both others must be 0. Otherwise, it's going to be smaller. You see it? I want to minus as much as I can. So I'm going to choose the K maximum beta OLSJ. Make these to be non-zero. And hence, what we have is this explicit formulation. This delta function, again, is an indicator function and this is the order statistics notation, the K. Said, you have seen it before, remember? On that night about that interview, I used this notation for you. Order statistics. This is nothing but order statistics. For Arab and Mahbuba, have you seen this order statistics notation? The K's smallest or biggest. So here, I define this K to be the K's biggest one. I'm gonna select this J, OLS J, if and only if its absolute value is among the K biggest one. Otherwise, it's gonna be 0. So this is the solution of the what? Of the best subset solution. And then let's compare this best subset solution with the Lasso solution. For the best subset solution, for the Lasso solution, what did we have? We are going to drop it by comparing the OLS absolute value of the OLS solution with what? With lambda. And as I mentioned, this is actually a soft thresholding, or you can call it a wavelet shrinkage. Why? Because the shape is like this way. If it's not in this area, it's 0. If it's in this area, it's itself. It's a wavelet. So it's called a wavelet thresholding. By contrast, what does best subset selection look like? It's a hard thresholding. Why? Because I don't want to compare you with any given parameter. I can just compare you with yourself. As long as you are not the top K, you are gone. That's it. You know what I mean? It's kind of like entrance exam. I don't know how about entrance exams in your country. Entrance exam in China is like score-based. So if, for example, the score is 100, total 100, you need to be at least as much as 80, for example. So if you are 79, you are done. You are gone. That's it. You're going to go to another university. If you are more than 80, that's you. Here you go. It's the hard thresholding. Okay. However, somewhat hard thresholding is very, very fair. You know what I mean? It creates a very fair condition in which is really, really good. So, okay, so the biggest difference between, in terms of, the dropping, the thresholding from between the Lasso regression and the best subset selection is that the former uses a soft thresholding, which compares the OL solution with a given parameter, while the second one uses a hard thresholding. It compares with itself. Okay, and this is kind of like a comparison. So, let me see. Please allow me to extend a little bit more. I want to try to finish this. I want to try to finish at least the elastic regression, elastic regularization here. So, okay. Then let's in general write beta in this way. I give this one as a P rather than, a 1 or 2. Clearly, a Q, sorry. I put this part here as the power of Q of the absolute value of beta J. So clearly, if Q equals to 1, it is Lasso. Q equals to 2, it's ridge. So a natural question is, can I do something like a compromise between Lasso and ridge? For example, can I try, for example, Q equal to 1.5? It looks very beautiful. I may have, something between Lasso and ridge, right? Unfortunately, if you choose Q equal to 1.5, you're gonna fail. Why? Because if Q equals to 1.5, it's gonna look like something like this way. It's very difficult for me to draw it. It's gonna something look like this way. It's anyway. No. Let me first draw a box. It's gonna be so this, and the corner here is gonna be kind of like this. You know what I mean? it's going to be kind of like this way, not the corner. You know, it's like here you go, here and here. It's going to be something look like this. By something look like this, it makes what? It makes it to be differentiable. In other words, you will not have the Lasso property that it can have a function of variable selection. Why Lasso has the variable selection property? Because it's non-differentiable, remember? And we use the subgradient optimality condition to discuss the subgradient S so that we can do the variable selection. But here, if you let Q, for example, to be 1.5, then it's differentiable. So you can still use ridge. What's the difference? Why should you use 1.5 or let's say 2.5? What's the point? You can just use ridge. So this is the point. This is the problem. To solve this problem and also to make something like has both the property of Lasso and the ridge. By the way, ridge is good. First of all, later in terms of Bayes estimates, we're gonna see ridge is the best. And the second, excuse me, the second thing is that for ridge, in terms of shrinkage itself, the level of shrinkage of itself, ridge performance is better than Lasso. That's the motivation why people kind of like try to find a compromised model between Lasso and the ridge. In other words, we try to strengthen the shrinkage part of Lasso. Okay. By this, so not Tipashirani, what's the name? Hastie. Hastie is the first author of the ELS. Tipashirani, the second one. Hastie and Zhou, they proposed the elastic net regularization model in this way. So here, what they do is that they use a ratio alpha and beta to put the 2 norm and 1 norm. And after centering x and y's and after some simplification, you can see it's going to be something like this way. And you can simply see if I write the problem in this way, where lambda 1, lambda 2 between I should add one thing. That's lambda 1 plus lambda 2 equal to 1. I should, or let's say equal to lambda. Should it be equal to 1, 1, 1, 1 part? Anyway, whatever. And by adding this part, what we have is what? What we have is we have both ridge and Lasso points here. And another very, very important thing is that because of this, the function becomes what? Non-differentiable. See it? If it is non-differentiable, then what's going to happen? I'm going to have the Lasso property. In other words, I can select the variables. See it? And also because I have this part, so that I have what? So that my shrinkage of the Lasso will be improved. So in this elastic net regularization model, it's going to be kind of like a compromised model between Lasso and ridge, and both sides will be strengthened. And very recently, Rahul, during my visit to MIT, I discussed with Rahul, and I saw he also he actually gave us a report. He proposed a new model, which is something between beta 0 and beta 1, beta 0 and beta 1. And I haven't checked his paper. At that time, it was not finished. I don't know how about now. Probably it's already finished. And they claim that if that is the case, they can solve the problem, the issue between the Lasso regression and the MIQP. Remember by Bartimas and Rahul, the paper, that they use the MIQP formulation to solve the best subset selection. The good point is that it is kind of like more direct than Lasso. It directly gives you the subset selection, and it's an accurate solution. But the better point is that if the RSR, the signal to ratio, the signal to error ratio is not too high, then that method gives you a relatively low statistical behavior, which is what I'm talking about in here. Where's my MICP? Oh, no, it's here. Lecture 10. MIQP problem is here. This is the MIQP, quadratic mixed integer quadratic programming. The problem is that if it does not have a very high signal to noise ratio, then it's going to be wrong. So that if I propose it in this way, a combination of 1 and 0 norm here, the problem will be resolved. I don't know whether the paper is finished or not, but probably this is the truth. Okay, so that is everything about, except for the last part, which is the base estimates about lasso and ridge. That's everything about lasso and ridge, and also the best subselection. Please do carefully read the lecture notes. You do need to, calculate these kind of steps hand by hand, step by step, by your hand. Don't just verify it. Do not. This is in general, not only for this class. It's a very big mistake for many people that they just verify the textbook or lecture notes. And doing this, it's too easy for you to forget it. You need to really step by step do it by your hand. Okay. Sorry, I actually extended 10 more minutes about this. Okay. That's everything about today's class. Thank you very much. So next week we're gonna finish it, and then we're gonna start the very basic introduction about unsupervised learning. As I mentioned, we may need to add one more class or maybe a half class in next Monday, the same time. Good point is that since nowadays, we're doing everything online, so it might be easier for us because we may have more time about this. Because previously I thought that the last week of the lecture was, the last day was like April 15. I didn't expect, sorry, May 15. I didn't expect that on May 15 it's already the exam week. That's why when I calculated the progress of the class, there's something wrong, because I really, really don't want to drop PCA. PCA is too important, That's the reason why I may want to extend one class about it. Sorry about it. If, let's say, the time you have time confliction, please let me know ASAP. Now we have remote education. I think the time is relatively free, so that we may have another time to try to finish this course. That's everything. Thank you very much, and you have a good evening. Bye-bye.